Okay, then we can continue. For here, you can see that actually we have an example, and then we can do it together afterward. And I just will give you some summary for the design for the drainage. Actually, just follow this guideline, and you know how to design for your drainage width. Drainage gully spacing. Now for here, first of all, we should have the so-called the longitudinal gradient. That means there's a slope along the road. And then you will have your drained width. Drained width actually is the width of your road that the water will be drained away on the width of the road. Then you should determine the cross flow of your road. As I mentioned, 2.5% is usually the minimum cross flow. And then depends on the longitudinal gradient, you will have different value. Then, depends on the surface of the road, you will have different roughness coefficients. And then here, the divide in the two steps. Actually, if your gradient is larger than or equal to 0.5%, then you will go to the left-hand side. And then if your gradient is more than 0.5%, you will go to the right-hand side. And then if, say for example, if it is larger than or equal to 0.5%, if you are having the so-called normal road flow, that means you have a normal road design, then you should go for the chart 1A and then to take a look to the drained area. If you have a hard shoulder flow, then that's not a normal flow. It is for, say, for the expressway. Then you have the chart 1B. Then from the graph or from the chart, you should look out for the drained area, A. Then your unadjusted spacing of the gully will be equal to 0.01 divided by n and then times A divided by W. Okay? And then for the gradient, which is more than or equal to 0.5%, you will have the equation on the equation 4. Then you have L naught and then times 1 plus F times R minus 1. So L naught, F, and then R, you will look it up the values from the chart. You can see that for L naught, you will look it up from chart 2A and then 2B. Depends on normal row or half shoulder flow. And then for the F, actually it's the adjustment factor. You will take a look from the chart 3. And finally, you will have the so-called the chart 4A and chart 4B. Actually, it is, depends on the gradient again. You will take a look for that. And then to determine the design gully spacing, you will have L, which is equal to LU times 1 minus RF rating times 1 minus RF depth. That means you have your unadjusted spacing. Then you will have the so-called the consideration of the grading of the gully, and then depends on the depth blockage of the road. Then you will take a look at table 5 and table 6. And then finally, after you are determining the spacing of the gully, then you will have the final check of the overall, the flow height of the water. So for here, the flow height is actually equal to the flooded width and then times the cross flow of the road. And then the flooded width is actually equal to 1.34 or 1.67 for the expressway. And then actually it is equal to 0.97, 1.13, or 1.16 for the so-called the normal road. Actually depends on different area. Then you will consider the value. Then for here, if the H ultimate, that means the flow height is more than the curb height, then it's okay. If the ultimate flow height is larger than or greater than the curb height, then actually you may adjust the curve height, change it to like 150 mm. Or actually you may also can calculate the reduction factor on the so-called the Gaudi spacing. And then the value actually is equal to the curve height divided by 12, and then the flutter width, and then the cross 4 of the row. Okay? Now for here, actually, we have an example here. And then for here, actually, we can take a look for the way how to design for that. Now, first of all, we can follow the guideline here. So we need to have the G longitudinal, that means the gradients along the row. And then we should have the flutter width, and then we should have the cross 4, and then we should have the roughness coefficients, right? Then for here, first of all, we have the so-called west lantau area. So for the west lantau area, we should take a look to the table. Here, actually for the so-called the maximum flutter width. So you can see that for normal row, we should have 1.13 meter. And then if it is a hard shoulder in expressway, we should have 1.67 meter, okay? This is actually the maximum flutter width that we need to consider, okay? And then the flutter width, we take it to be 12 meter. And then for the cross 4, we take it to be 3.6 meter. 3.6%. And then for the longitudinal gradient, we take it to be 1.5%. While for the surface, we take it to be bituminous very coarse. And then for the curve height, actually it is 125 mm. For the blockage problem, we have the near amenity area and the non-spot black spot. Now for this one, we need to take a look to the n value because it is the surface coefficient. We need to take a look for that. So we can go back and take a look of the values of n. Now it actually means that it is bituminous very coarse. So n we will take 0.013, okay? So you can go back here and then we can take n is equal to 0.013. And then for the blockage, it's actually near amenity area, and then it is not the black spot. Then we can take a look. Like it actually is the normal row, and then the gradient is 1.5%. So for here, we can take a look to the reduction factor for the debris. For the gradient, actually it is equal to 1.5%. 1.5%, that means the longitudinal gradient is larger than the 0.5%. So we should use this one, right? It is the normal row, and then the longitudinal gradient is 0.5% or more. Therefore, here actually it is near amenity area, but not small, not black spot. So the reduction factor is equal to 20%. Do you agree? So this one, the RF debris will be equal to 20%. Agree? So we will follow this kind of data and then to have our design. But for the Gaudi type, actually GA1 450, so it depends on the pattern. We should have this one, and then the GRF rating is 0%. So the RF rating should be equal to 0%. Do you agree? Okay, then we will have the all the data, and then we can follow this guideline. But we have already our G longitudinal, that means our longitudinal gradient. And then we have our Hutton wave, and then our phosphor is also given. And then for the roughness coefficient, we have determined, actually it is bituminous varying cost, so actually it is 0.013, right? For the step 2A, that means it is the longitudinal gradient is larger than 0.5% because it is 1 point something. Then we should use this equation. Do you agree? This equation is 0.01 and then divided by n and then times A divided by W, right? Do you agree? Then it is the normal row, so we can take a look to the chart 1A. W is equal to 12 meter. Then we can take a look to the chart 1A. Then we need two data. One is the longitudinal gradient. The other one is the phosphor. So we can find together. Please tell me what is the general calculation for the area. Okay, we should do this one. What is the phosphor? What is the values of the phosphor? Phosphor is down. The time of phosphor is down. What is the values of phosphor? Okay, 3.6%, assuming it is here. Okay, 咁我 longitudinal gradient 幾多？ Okay, 1.5. Then we are using this one, right? So we are considering 3.6 here, and then 1.5 is a longitudinal gradient. Now we do it together, okay? Take a look to the design 1A, and then for the general calculation for the drained area. So we will use this graph, this line. We consider this one, okay? Do you agree? Then we can use this graph and then we just go up. Okay, it is the line for 1.5. It is around 160, right? So it is actually 160 meters squared. Okay, so the drained area is 160. This is for the chart 1A, right? So A is equal to 160. So we use this equation, LU is equal to 0.01 divided by N. So LU is equal to 0.01 divided by N is equal to 0.013. And then divided by A divided by W. A we just have 160, W is equal to 12. Right? So we just calculate 0.01 and then divided by 0.013 and then times 160 divided by 12. Do you agree? Then we just use our calculator. Okay, then I can calculate it's around 10.2 or 10.3 meter. Right? You agree? Okay, then after that, you will have the L, actually it is the design spacing, which is equal to LU times 1 minus RF grating, and then times 1 minus RF depth. Then L is equal to 10.3 times 1 minus 0, because the rating is actually equal to 0 for our type of the Gaudi. And then for depth, it's actually it is 20%, so it is 1 minus 0.2. So it is 10.3, and then times 1 times 0.8. Am I correct? Then actually it is equal to 8.2 meter, right? This is the design spacing of the Gaudi. Then finally, I need to check for the ultimate or the flow height of the row. It is equal to 1.2 and then times 10 and then times cos 4. Cos 4 is 3.6%. And then times what? And then times x4. X4 is still 3.6%, and then ultimate. But for the ultimate, actually it's the ultimate flow width actually depends on the row. So you can see that actually it is the west lantau area. Then you can take a look to the values of west lantau area. West lantau area is here, and then you can see that for the normal row, actually it is equal to 1.13 meter. Do you agree? Right? So it is 1.13. Sorry, it is 3.6. And then this one is 1.37. West lantau is 1.13. Okay, this one, okay? So actually this 1.2 times 10 times 3.6 and then times 1.13. Then actually this is equal to 48.8 mm. Okay, then this one is more than 125 mm. So actually this is okay. So that means the spacing of 8.2 meters should satisfy the requirement. You know what I mean? Right? So actually the calculation is not very difficult. You can see that basically all follows the chart. Well, first of all, you will find the so-called the n value actually depends on the road surface. Then you can calculate and adjust the spacing of the gauge. And then you will consider the so-called the dampness and then the grating of the gauge. Then you will find the so-called the design spacing of the gauge. Okay? And then finally, we will try to find the so-called check with the overflow or the overtopping, whether you can satisfy the requirement. And then finally, once you put the values right there, it's 3.6 of the phosphor, and then the design plug width is 1.13 meter, then you can calculate the flow height, which is smaller than the curb height. Then that means your gauge spacing should be fine. So for this one, actually has already satisfied both the ultimate state condition and then the serviceability state conditions. Okay. So this one actually is relatively easy, as I can say. Basically, it just follows all the criteria, and then you just check it from the chart, and then you can determine the so-called the gauge spacing. Now you can go home and then take a look by yourself for this one. And actually, in the tutorial, I think I give you the one, it should be the one in the head. Okay, it's the same. So the problem is the same for in the tutorial sections. And then there's another one, actually design the Gaudi in normal row. And then you can see that I have changed the gradient to 0.4%. And then for this one, actually, you can use another equation because the one larger than 0.5% will be one equation, and then the one less than is another one. Okay. So right now you can try by yourself to use those guidelines and then to choose. To try question number 2, and then see whether you can get the answer or not. Okay. So you can try it by yourself right now. 你自己試下。So you can follow the step here. You have the longitudinal gradient, you have the generated wave, you have the cross-flow, and then you have the end. Because actually the longitudinal gradient is more than 0.5%, then you can follow the right-hand side, and then to find the so-called L0, F, and then R from the chart 2A, and then from the 4A. And then because actually it is another area, so you can find the flooded width and then check for the step 5, okay? So right now you can try it by yourself. Okay.
I would like to arrange a meeting for this month with Civil Society. Is that okay?
Yeah, sure. Just let me know when you want to.
The year 2 students, I'm not sure whether they finish their midterms. Have they?
It is the normal row, and then actually you can see that the longitudinal gradient is less than 0.5. Then again, we may use 20%, right? Then it is GA1 450. Again, the RF rating is equal to 0%, I think, right? Do you agree? Okay. Then we will use the equation. Let's share. Okay. Okay, share funding. Okay, then we will use the equation here. L naught times 1 plus R, F times R minus 1, right? So we will use the equation LU is equal to L naught times 1 plus F R minus 1. Right? So L naught, we can find it by the chart 2A. So actually it is the one here, right? We are not for the hard shoulder. We are for this one. Then we have the jointed width. Actually it is equal to 12 meters again. Then the cross floor will be equal to 3.6. So around 3.6 is something like that. And then the jointed width is around equal to 12. It's around the value, okay? So maybe you can assume that it is 7, okay? L naught, 7 meters around. Of course, if you have a ruler, then you can do it more precisely, okay? Do you agree the jointed width is 12 meters? Because we have the jointed width is equal to 12, right? And then the longitudinal, the cross floor is equal to 3.6%. Then around it is equal to 7 meters. Of course, if you have a ruler, then you can do it more precisely. Then you can determine the F. If you go back to the equation, the F you will determine from the chart 3, right? So go to the chart 3. This is the chart 3. So it depends on the jointed width, it is around 12 meters. And then you can take a look to the adjustment factor, it is around 0.5, right? So F is around 0.5. Agree? And then finally, you will determine the R. R will depends on the chart 4A here. So you will go to the chart 4A. Then you can see that your longitudinal gradient is equal to 0.4, so you use this 0.4 here. And then your cos 4 is equal to 3.6. So around you draw a 3.6 here. So your value is something like that here. And then your values is in between. So around it is equal to 1.13 or 1.12. So this R is around equal to 1.12, right? So you just multiply all these factors. Then you will get the values of around 7.4 meter. Okay? Then of course this is the undisturbed or unadjusted value. Then the design value of course is equal to the LU times 1 plus RF, that is, and then 1 minus RF rating. This one we have already found that is 20%. This one found that is equal to 0. Right? So again, it is equal to 7.4 and then times 80%. Around is equal to 5.9 meter. Right? Can you get that by yourself? 你自己計唔計到啊？ And then finally, you will check the ultimate height, flow height of the road. The ultimate width, we just checked that is equal to 1.16. Depends on the type of the area. And then the cos 4 again equal to 3.6%. Then actually you will have the value is equal to 50.1 mm, right? So actually it is again more than 125 mm. It's more than your cut height. Do you agree? So, well, it is okay for your Gaudi space, right? So this one is not very difficult because actually just follow all the graph, all the charts, and then the equations. Then you can find all the answer. Okay? Okay, so that's it for the chapter today. Okay? And then we will have our final chapter next week, which is about the lighting of the highway, okay? And then we will have some final revision next week. Okay, any questions before I end the lecture today?好啦，各位有冇問題 ？OK， 如果冇問題咧，我就先到呢度啦。OK， 咁樣就下個禮拜就會有啲重點同大家温一温嘅，好嘛？咁你哋考試嘅時候就即係温一温啲重點啦。咁我會俾一張紙你哋自己可以帶入去，即係抄咗帶入去啦，因為就比較多嘢，我驚你哋一陣間話記唔晒，你寫少少 note 上去啦。咁就一張紙前後你可以寫 A4 字，好嘛？咁你都要記住啦，我都基本上有啲 chart 要你 plot 嘅，頭先我都講過啦，即係話你嗰啲 muscle design 啊，嗰啲 chart 你都要識 plot 啦。咁揾翻個 optimum 嗰個 bitumen，OK？咁冇問題咧，咁我哋就到呢度啦，好嘛 ？OK，咁下個禮拜見，拜拜。